Okay, all right. So thank you for coming, Mai. We're really excited. So just to introduce Mai, Mai is a final year PhD in computer science at Stanford University, advised by Professor Christopher Wray. Her research focuses on the fundamentals of AI through data-centric approaches, particularly in training data curation, via techniques she has developed in data mixing, curriculum learning, and weak supervision. She has a myriad of awards. Her work has been recognized in as a best student paper runner-up at UAI, a best paper award at AAAI, and spotlights at both iClear and NERVS. And we're really excited. So whenever you're ready.
Okay, thank you for the introduction and thanks for having me here. So today I'll be presenting some work on data mixing throughout language model development. And this was work I did at my internship at AI2. And this was kind of the data mixing that was used for the OMO3 model. Okay, so to start with some basics, data mixing is the procedure of figuring out the sampling ratios across different data sets. So you combine data from different domains to create a training data set that results in your model exhibiting a broad variety of capabilities. And more generally, I want to emphasize that data mixing is kind of everywhere if you're trying to develop data to train a model. So you can mix on different languages, you can mix across like quality scores, you can mix at different stages of training, not just pre-training. So basically, whenever you have more than just one data set, you inevitably need to decide the ratios of this data mix. And in addition to mixing kind of being everywhere, it's also quite important. So as a teaser of our results today, here's a figure that shows that training on a good mix can result in a 12% improvement in downstream task performance, and it allows you to arrive at the same performance 3 times faster than training on a baseline mix. So you can see that mixing here can really make a difference. However, the key challenge with determining a good data mix is that this naive approach is just brute force search or tuning these ratios manually. And so requires a lot of trial and error and can be quite expensive. But fortunately, we're at a point in the literature in the field where there's a lot of existing methods that have been proposed to learn these mixes more efficiently. And so in this talk, I'm not really going to focus necessarily on proposing a new algorithm, but I'm going to focus on talking about issues that arise in data mixing during large-scale model development. So take this timeline here. So you're here on the left. You're maybe a few months or weeks out from the day you want to start training your big model, and you have your domains, your data sets, and you need to figure out the data mix. So the first question is going to be, how do I get a good mix on these domains that I started out with? And it's not super clear here. So should I just run some existing mixing method out of the box? Should I kind of design my own method, make some adjustments? And so that's the first challenge. And this is kind of what the challenge we faced at the start of building OMO3. And that moves on to the second challenge. So suppose you figured out your initial data mix and you think it's great on your current set of data. The second challenge is that data is constantly changing throughout model development. And that's just kind of reality, is that people are constantly collecting and building new data sets. They might be reformatting things, filtering things. And so the question now becomes, how do you maintain a good data mix throughout development as these domains evolve? Like as an example, suppose we have a good mix and someone adds a new data set. What should our new mixture be? And can we determine it efficiently? So as an overview of this talk, I'll be going over our contributions in 2 parts. So the first part is sort of a practitioner's handbook to data mixing. So we did this comprehensive study of a lot of the design choices you need to consider when constructing a data mixing method. And then the second part is going to be a method we introduced for using information from existing mixes to efficiently recompute the data mix as data changes throughout development. So let's get into the first part. So I'll give some background on just the classic data mixing problem. So we have M training domains D1 through DM, and we want to train a model of S parameters on R tokens in total. And the data mix P is a probability vector over the M domains. And the final mixed training data set is created by sampling R times P of I tokens for each domain D of I. We then denote this LM of SRP as a target model trained according to the data mix P, and we're going to evaluate this trained model on N downstream tasks. Here we chose to measure bits per byte, also known as BPB, where lower is better. It's kind of like a scaled loss in some way. And the goal in data mixing now is to efficiently find the mixture P that minimizes the average BPB over all the downstream tasks that we identify. So there's a ton of methods that aim to solve this problem I've just described, but a lot of them actually follow this pretty general template that's quite simple and effective, which we'll call the offline mixing schema. And this procedure has 3 steps. So the first step is that we train a bunch of smaller models, we call these proxy models, on different data mixes, and then we evaluate each of these models on the tasks we care about. So we're refer to this as a swarm of proxy models. And you can think of this as a way to explore and do like very lightweight trial and error. So if I try this data mix on a really small model for like a few tokens, or not a few tokens, but like a relatively small amount of tokens, what performance will I get? Then second, using this swarm, we're going to fit a regression model that learns the relationship between the mixing ratios and the performance. And so this regression model, this F hat of P, it's going to allow us to predict the performance of any candidate data mix. And then finally, we propose a mix by solving an optimization problem that uses the regression model as a surrogate for true downstream performance. So basically, we find the mix that has the best predicted performance. And so these are the 3 steps of the offline schema that many methods follow. And so the question is, how do we create a good mixing method that follows this general procedure? So first, by examining this schema, we came up with a big list of questions that a practitioner needs to go through in order to define a mixing method from this general procedure. So this is kind of, you can think of this as like a checklist. So in constructing the swarm, you need to determine how big these proxy models are and how many you need. You also need to determine the distribution you should sample the mixes from for this swarm. Then for the regression fitting step, one obvious question is what regression model should you use? Should you do something linear, nonlinear, non-parametric? And also like what should your regression targets be? So should you fit one model for each task? Should you fit one model for each like task family? And then the final thing for the optimization stage, we need to figure out how to handle the fact that data is finite and we don't want to repeat samples too much. And we also need to figure out how do we actually like numerically solve the optimization problem. So this is a large but non-comprehensive list of kind of like all the decisions a practitioner needs to make. And before we dive into how this paper answered the questions, I wanted to show first this table of how existing methods answer all of these questions. So each row here is each of those questions are design choices I just mentioned, and then each column is an existing paper. And so there's kind of 3 observations here. So first, any pink cell means that we were able to find justification for their configuration. And unfortunately, there's a lot of white cells, which means that many of the design choices in existing literature lack guidance beyond the specific instantiation. Second, even the rows that have a lot of pink cells tend to lack consensus. So for example, each existing method proposes a different regression model and reports strong regression fit to support it. And this conflicting guidance makes it hard for practitioners to determine what model should we actually use. And then finally, all of these existing methods here kind of fail to address practical issues like handling data repetition constraints in the second from last row. So you can see there's a row of no's just across the board. So we've established that these design choices are not well understood, and so we're going to try to answer each of them ourselves. So for our setup, our target models were 1 billion parameters and trained on 100 billion tokens. And we experimented mainly on DCLM baseline, a web corpus that was partitioned into 24 topic-based domains. So things like literature, politics, science, fashion, so on. And we measured BPB, bits per byte, on a suite of 52 tasks that covered math, code, and question answering. And so due to time, I'm just going to go over a subset of the design choices. The rest of them are in the paper. So the first one we look at is proxy model size. So how small can these models in the swarm be so that they still provide good signal for the 100 billion parameter target models? And it's not really clear what size to use. Existing methods go from 1 million parameters up to 400 million parameters. So to study this, we took a bunch of data mixing ratios, and for each mixture, we trained both a proxy model and a target model on them. So a small model and a large model. And then we looked at the performance rankings of these mixtures at the proxy scale and at the target scale, and we measured the rank correlation. So we're trying to see that if the data mixtures that did the best on the small models also do the best on the large models. And we repeat this experiment for a bunch of different proxy model sizes. So here are our results. So on the x-axis is the size of the proxy model. So we did 1 million, 15, 30, and 60 million. And on the y-axis is the rank correlation with our target 1 billion parameter model. So we can see that everything over 15 million parameters has a pretty high rank correlation. So our recommendation, at least if you want to do well at the 1 billion parameter scale, is to use proxy models that are at least 15 million parameters. So the next question is, how big should the swarm be? So concretely, if we have M domains you want to mix on, how many proxy models do we need? And again, existing works give many different recommendations, and most of them don't provide a general formula, but instead are just saying, okay, for this set of domains, we use 512 runs. For this other set, we use 20 runs. They don't really provide this formula. So for our experiment, we are going to basically measure the sample complexity. Oh, yes, I see a question. The hyperparameter configuration across the proxy models is going to be slightly different. Oh, I cannot go back. Let me see. Yeah. The proxy model configurations are slightly different. We use a scaling law for like the learning rate and the batch size. Hopefully that answers your question. We can talk about it more. Um, okay. So yes. So going back to the number of the swarm size, we're going to measure the sample complexity or the rate. Yes, question?
Sorry, I think your screen got a little cut off at the bottom.
Oh, I'm sorry. Is this
Yeah, that's
better?
perfect. Thank you so much.
Okay. Um, awesome. Okay. Yeah, so we're going to measure the sample complexity or the rate at which increasing the number of swarm runs helps performance. So for a fixed M number of domains, how many of these proxy models do we need to get performance within a certain margin of the optimal or best mix we find? So in this box here, we look at domain sets of size 6, 12, 18, and 24. And then we vary the number of runs k, so we scale it linearly in terms of the number of domains. And for each of these m and k, we'll train a model, look at its performance, and report the error as its performance versus the performance of the best mix we found overall. And that's kind of our approximation of like close to optimal. And so this figure here shows this sample complexity. So on the x-axis is the swarm size, where we've scaled everything to be not the absolute swarm size, but just the size relative to the number of domains. And on the y-axis is that error, so how close we are to the best mix we found. And the thing to notice here is that across all of these m's from 6 to 24, the curves all look pretty much the same. And so this indicates that the error only depends on the swarm size relative to the number of domains. This helps us arrive at the conclusion of linear sample complexity. So you just need O of M proxy models to learn a good mix over M domains. The next question is, what regression model should we use to capture the relationship between the data mixing ratios and the downstream performance? So to study this, we are going to take a swarm and try 5 different regression models on it. And we'll measure how good the regression fit is, and we'll also measure the final performance. The regression models we consider range from gradient boosting to Gaussian processes to the last 3 here being parametric functions. So first, we measured how good the regression fit is of each of the models we consider, and we looked at how this depends on the swarm size. So this reveals something actually pretty interesting, which is that different models, different regression models excel at different swarm sizes. And this potentially explains why there's a lack of consensus in the literature on which regression model to use. So for instance, BiMix is quite good for small swarms, while light GBM, the gradient boosting, needs a lot of proxy runs. But to figure out which one we actually want to use, though, we notice that the log linear models in purple outperforms the other models consistently when you have at least 75 runs. So basically, once you have at least 3 times the number of domains, this purple line kind of dominates. And now let's look at downstream performance as well. Here, remember, lower is better. So previously we saw that log linear had a good regression fit, and now we also see it has the best downstream performance. So our takeaway from this is that we decided to use the log linear regression model moving forward. And I'll provide an exact equation or form of it later. And so the last design choice we'll look at is how to handle data constraint settings. So let me first explain what this means. So in the chart here, we're considering a scenario where we have web, math, and code data, and the y-axis is telling us how big each of these domains are, let's say in trillions of tokens. And so given a data mix, the mix translates into a certain amount of tokens we need to sample and give to the model to train. And so suppose we request 5 trillion tokens of web data, and that is all fine because we have enough web data lying around. Next, let's suppose we request 2.5 trillion tokens of math data. And so now this gets a little bit dicey because we don't have enough data, but that's okay. We can just repeat math samples an average of 2.5 times. And now finally, let's suppose our mix requests 4 trillion tokens of code data. And this is where we get in trouble because we would need to repeat code samples an average of 8 times. And this is way too much, as prior works have shown that repeating past 4 or 5 times starts to degrade the performance. So it's incredibly important to produce data mixes where we aren't excessively repeating samples. So the question becomes, how do we enforce repetition caps in the data mixing problem? And unfortunately, none of the existing works we looked at really address this. So they usually assume that you always have more data than you request. So for our experiment, we wrote down this repetition constraint formally in the bottom left here. So basically, this constraint says we do not want to sample more than k times from any domain. And so this constraint encodes that as a function of r, which is how many tokens we need, and n of j, which is how big your domain is. And our experiment involves considering 3 ways to add this repetition constraint. The first way is to add it to the swarm. So basically, we ensure that all the proxy models are trained on mixes that follow this repetition constraint. The second way is to add it to the optimization. So we can just add on this constraint pretty easily since it's just a linear constraint. And then the final way is to add it to both the swarm and the optimization. So our results show that approach 2, where we only add the repetition constraint to the optimization problem, achieves the best performance while producing a mixture that satisfies the repetition constraint. And in the figure here, I've also shown how the proposed mix depends on the repetition factor. So you can see that as we vary this repetition factor k from 2 up to infinity, which is basically unconstrained optimization, the proposed mixes can change a lot, um, especially, for instance, like the science, math, and the software domains. And so this is a very important piece of the mixing method. Like this constraint can really shape what the final mix you use is. So after studying all of these design choices, we used our findings to define a base mixing method for OMO3. So we called that Olmix base, which is kind of our recommended default configuration of the offline mixing schema. So recall the first step, which is constructing the swarm. We ended up doing it with 30 million parameter proxy models, but anything above 15 million we showed was fine. And we generally do O of M proxy models. In the regression model step, we decided to fit one log linear model for each task. And here I've written out that exact form of the log linear function. And then finally, in the optimization step, we optimize the average predicted performance, but now we add a constraint to ensure that the proposed mix does not excessively repeat samples. And so that summarizes the Olmix-based procedure and kind of the first part of the work. So now I'll move on to the second part, which is mixing under evolving data. So this is a pretty novel problem setting, but was motivated by what we encountered in practice, which is that data is constantly being updated throughout development. So I made this, meme to describe the feeling. So you're a practitioner, you think, I finally have a pretty good mix on these data sets. We can start training things, we're ready to go. But then the data changes. So either someone on your team finishes preparing a new data set that's really good and needs to go into the final mix, or you actually just figured out that you should more aggressively filter one of your existing domains. The reality is that these sorts of changes are always happening when you're trying to create the best data for training. And so the question is like, what do you do with this mix that you've prepared on the old data sets? Like, do you have to throw it out or can you reuse it in some way? And to further add evidence that this is a real phenomenon in model development, let's take a look at the pre-training data sets for OMO2 versus OMO3. So you can see that over the course of a year or so, there have been changes to the pre-training corpus. So of course, some of the domains were the same. So archive and Wikipedia are still there, but some of the domains are gone now. So algebraic, stack, and pesto are in OMO2, but not in OMO3. And we also see that there's some new domains in OMO3, like the OMO CR science PDFs. And then finally, there are some domains that are revised or modified. So for instance, the code source changed from StarCoder to StackEDU, and the math source changed from Open Web Math to FindMath. So now I'll formally describe the problem of mixing as data evolves. So we'll start with a domain set D of M domains, and this is updated into D prime, which consists of M prime domains. And based on our experience, we found there were four major ways that D is updated into D prime. So we have addition and removal. So these are pretty self-explanatory. You have a new data set or you throw out one of your old data sets because it's maybe not of sufficiently high utility. We also have partition, where we take a data set and we're able to annotate it such that we now have finer grained categories. And lastly, we have revisions, which is when we replace an old version of a data set with a newer version. So this could be filtering or rewriting or things like that. And so our goal in this setting is that we have an existing mix, T tilde, on the old set of domains D, and now we want to figure out the optimal mix Q star over the new domains D prime. So I'd like to emphasize here that this is basically the same objective of data mixing as before, but it's just written over Q now. And we also added the repetition constraint because we determined that's something that we should almost always have. So how do we figure out what the new mix over D prime should be? Before I go into our method, I wanted to present a simple baseline, which is full recomputation. So this means we just apply a mixing method. So this could be Olmix base or anything of your choice directly to D prime every single time the domain set is updated. The problem with this is that it becomes expensive quite fast. So if the data changes a lot through development, this means you're constructing a swarm of size O of n prime every single time. And so full recomputation is not the best. It should have pretty good performance because you're relearning everything, but it's very costly. So instead, we're going to see how we can reuse that existing mix p tilde so that we don't have to relearn everything whenever data changes. So to explain our method, which we call mixture reuse, we'll look at this example of partitioning. So you start out with 4 domains, and then the fourth one gets partitioned into 2 subdomains, D4 prime and D5 prime. So let's give some names to these domains. So let's say we start out with science, politics, literature, and code, and then code gets split up into Python versus not Python. And suppose we have these existing p tilde ratios over the initial 4 domains. And let's take a closer look at the normalized ratios of the first 3 domains, which are not impacted by the partition at all. And the core bet we make in this mixture use idea is that these normalized ratios are still good to use after code is partitioned. So basically, we're assuming that the fact that we now have Python versus non-Python to mix over is not going to change the relative ratios of science versus politics versus literature. So let's get into the method now. So we take this D prime and we're going to split it into 2 subsets, dfix, which are the domains that weren't affected by the update, and decomp, which are the domains affected by the update. And the first thing we'll do is we freeze the ratios within dfix, basically treating dfix as one giant virtual domain. And then rather than recomputing the mix over everything, we're only going to recompute over what we call the collapsed mix, which is the single dfix virtual domain, as well as the affected domains in decomp. So in this example, rather than learning a mix on all 5 domains, we're just going to learn on 3 domains, which is a simpler and cheaper procedure. And then finally, once we've learned the mix on 3 domains, we're going to use the frozen ratios to expand the learned mix back to D prime. So let's look at a quick example. So recall that here was our p tilde as well as the normalized ratios within dfix from before. And let's suppose that this second step of recomputation gives us a mix of 0.6 on the entire dfix virtual domain and 0.25 and 0.15 on Python and non-Python. So then we can construct the proposed mix by multiplying 0.6 by those normalized ratios above and just tacking on the recomputed mixes. So this procedure is essentially applying any data mixing algorithm in a lower dimensional slice of the mixture space. And the main thing this allows us to achieve is that there's less recomputation required. To make this a bit more concrete, I'll describe the implementation a bit more. So how do we apply Olmix space, which I presented just now, into this lower dimensional space? So first, we'll train a bunch of these proxy models on different swarm mixes. And here, notice that all of these swarm mixes have the same frozen ratios within dfix. And next, we're going to fit the log linear model on the collapsed mix, which is just the 3 domains. And then finally, we're going to figure out the optimal collapsed mix, and then we expand it back to the 5 domains by multiplying the collapsed mix by the frozen ratios. So you can see that this is very similar to the original Olmix-based procedure, but we're just sampling those swarm mixes different, and then we are doing this sort of expansion step at the end when we get our final mix. And so we can see that full recomputation and mixture reuse are 2 very different approaches. So while full recomputation relearns everything, mixture reuse recomputes over fewer domains and results in a lower cost. So the big question now is, when is the performance of full mixture reuse close to full recomputation. You can imagine that if our existing p tilde was straight up terrible, the mixture reuse won't do very well because you're reusing bad information. And so the next few slides will kind of focus on understanding this a bit more. So getting into the analysis, we have a series of theoretical results that you can look at more in the paper that go over when mixture reuse does as well as full recomputation. I won't go too much into the theory, but I want to emphasize that the exciting thing is that we have empirical results that closely track this theory. So our first result is that the performance of our approach mixture reuse is close to full recomputation when the ratios we reuse are good. So very simple. Good here means that the reused ratios, that p tilde, is close to the optimal ratios on dfix after the update. And so in the figure here, we can see that this is empirically supported. So on the x-axis is the distance between the reused ratios and the optimal ratio after the domain update. And the y-axis is the performance gap between mixture reuse and full recomputation. And so we can see that as the reuse ratio gets farther away from the optimal ratio after the update, the performance gap also increases. So the key takeaway here is that the performance of our approach is controlled by how good the p tilde is. And so the next natural question is, well, when is this p tilde that we're reusing good? And so our result says that the reuse ratios are good when the affected domains do not interact with the existing domains. So basically, the domain update doesn't really interact with the things that are not updated. And the paper has a more formal definition of what I mean by interact, as well as a more formal theorem statement. But to validate this, we are going to look at a case here where the reused ratios are bad, and that's because of this interaction of the affected and unaffected domains. And we'll show this by showing that changing the dfix versus the decomp will improve the reused ratios. So here, let's consider a case where we start with the topic domains from the DCLM baseline, and we add in some stack edu code data. So the bar graph here shows how the reuse ratios over DCLM compares to the optimal ratios over DCLM after the update. And in particular, you can see that the ratio for software development in DCLM is really far off from optimal. And our claim is going to be that this is because the added code data, the added stack edu data, interacts with the software development data. They're basically all impacting the model's coding abilities. And in the next few slides, we'll validate this by presenting an extension of mixture reuse that changes how we split dfix versus decomp. So recall that in standard mixture reuse, we split this d prime into a set of frozen ratios dfix and a set of ratios to recompute decomp, where dfix contains all the domains unaffected by the update, and decomp contains the domains affected by the update. And instead, our extension, which we call partial mixture reuse, only reuses some of the unaffected domains, and it actually recomputes the other unaffected domains along with the affected ones. So in the diagram here, all we did is we just moved that software development topic of DCLM from the frozen ratios to the recomputed ratios. And this means we're just going to learn its ratios along with the stack edu ratios. And this results in dfix being a smaller set of domains, and we effectively recompute the mix on more domains. So let's see how this actually does. So going back to our results, this first figure here is showing that the reuse ratios from the full mixture reuse are quite far from optimal. But however, for partial mixture reuse, once we stop reusing the weight on software development, we can see that the reuse ratios are much closer to optimal. And this difference in quality is reflected in the performance gap, where we see that the partial mixture reuse is able to get much closer to full recomputation than full mixture reuse. And so the core takeaway here of this sort of analysis is that we can control performance of this mixture reuse idea by choosing what domains we want to reuse the ratios on. So taking a step back and looking at all of our strategies, we have full recomputation, the baseline, partial mixture reuse, and full mixture reuse. And we can see that partial mixture reuse requires a little bit more recomputation than full reuse, but it's generally able to achieve better performance. And it's kind of, we're showing that there's this sort of spectrum of recomputation strategies. So finally, we'll get into some of the results. So to evaluate all of these reuse settings, we're going to simulate a realistic development scenario, kind of like what actually happened when developing OMO 3, where the data evolves over 5 updates, and we end up with a final data set of 64 domains. So we first start with a web dataset DCLM split into 24 topics. Then we'll add in 15 domains of Stack EDU code data. Then in the second update, we'll add in 6 other sources of data, so archive, math, PDFs, and so on. The third update will revise the science PDF data, where we change how the format is done. In the fourth update, we'll remove this domain algebraic stack since it wasn't super helpful. And then finally, we'll partition the science PDFs into 21 topics. So this gives us 64 domains at the end of the process, and we are going to train 1 billion parameter models and evaluate them over our 52 tasks and see what is an efficient mix that we can do in this process. So we'll go over some methods we consider. So our main baseline is the natural distribution, which is just to mix proportional to the final domain sizes. So you can think of this mix is what is induced if you just concatenate all your data sets together and like randomly uniformly sample from that. We also consider full recomputation, which applies Olmix base to all domains after each update. And so that's going to be very expensive, but hopefully have a good performance. We also then finally we consider full mixture reuse and partial mixture reuse, which are our 2 methods. And so our first result is on the performance versus cost trade-off. So on the x-axis is the total number of proxy runs that the method uses throughout the 5 updates, so some notion of cost. And on the y-axis is the percentage performance improvement over the natural distribution. So methods that are in the top left corner are the best, so cheap and performant. And each method here, we do 3 random seeds. And so first, if we look across horizontally, we see how mixture reuse does compared to full recomputation. And we find that we achieve between 95 to 98% of full recomputation's performance while using around 67% fewer total proxy runs. So we use around 200 something runs compared to full recomputation's 800 something runs. Next, we can look vertically to see how all of these methods do when we fix the budget. So at a budget of around 200 to 300 runs, mixture reuse achieves 12% improvement over the natural distribution. And on the other hand, full recomputation achieves an average of 10.8%. And then we also look at the absolute results. So how good is the best mix we have from mixture reuse? Basically, how good is data mixing overall? And so compared to the natural distribution, our best mix that we got efficiently was 12% better on downstream tasks and 3 times more data efficient. And this was the figure I had shown earlier. And then last, we want to kind of validate our method by comparing the proposed mixes. So ideally, the proposed mixes should look similar to the full recomputation mixes. And we can see that our proposed mix is more similar to full recomputation than the natural distribution, which aligns with the downstream performance results from the previous slides. So you can see that both full recomputation and partial mixture reuse tend to upsample things like Python data and like code and math. Yeah. So to wrap things up, our paper Olmix has 2 main contributions. So first is a study of the core design choices needed to configure a mixing method from the offline schema. And then second is a mixture reuse method that allows us to efficiently recompute data mixes even when the data changes throughout model development. So as some future directions, I just listed three. So the first one is online mixing. So right now we're talking about how do we construct a static mix that we can use throughout model training. But it would also be very interesting to see what are the key design choices for online data mixing and like how can we incorporate both online in the mixture weights as well as online in the sense of the domains themselves are changing. The second future direction is co-design with other data development stages. So mixing and other stages like curation and deduplication, all of them are, intricately um, intertwined in a sense, and you can use, data mixing to even like probe how useful different slices of data are. And so kind of like figuring out the right feedback loops for that. And then finally, automating partial mixture reuse. So currently, I said that we can choose which ratios to recompute on, but that's kind of currently just practitioner's intuition. So if you see that you have code in your reuse domains and you add in a bunch of new code domains, the practitioner rule of thumb is you should recompute the code domains, but we don't have an automated way of doing this right now. So that's a future direction. Um, and so that kind of wraps things up. I have all the, contact information and all my collaborators here, and I can take some questions now. Okay.
Thank you very much, Maya. That was awesome. I think Jiashi has a question. How do you compare data mixing with data selection?
Yeah, that's a good question. So I think mixing I see as a very coarse way of controlling the data distribution. And I see data selection as a much more fine-grained way of shaping the data distribution. But I do think like, yeah, there's like ways that you can kind of like combine them or like one example of how you can combine mixing and selection is like right now when you have mixture ratios, you say like sample from this domain with a ratio of like 50%. Most of the time you just randomly select samples from that pool. But you could actually do things where you only select the 50% of samples you select are like the top 50 scoring in terms of some quality filter or something like that. So there's a lot of ways to intersect the two, which I think is pretty exciting and would be interesting to look at. Okay, I see Eugene has the question. So can we apply existing mixing strategies from pre-training to post-training, and what are the unique challenges there? Um, that is a good question. So I think there's two challenges based on what I've kind of seen. So I did a little bit of mid-training mixing as well. So, kind of in between the two. And I think one challenge is that I'm not completely sure how nice the regression models fit. So I think during pre-training, when you initialize models from scratch, they all have very nice behaviors. And so this sort of like log linear function or these sorts of like power laws, like linear combinations of power laws that are very common in pre-training literature, those fit really well for pre-training. But I've seen that, once you try to apply those sorts of functional forms to post-training, I think the post-training results just tend to be a lot more noisy because your model already has some base knowledge. And so the new data coming in also interacts with that. And so the regression models are not necessarily nice and linear, is my main hypothesis. I've kind of seen some of that, but I don't have a good idea of like what the right parametric model is, or we need to move to more complex models. And then I think the second thing is that I don't think it's necessarily clear how to do the like, I think a lot of data mixing and just pre-training work in general relies on the fact that you can train a bunch of small models easily, and that insights from small models like transfer quite nicely to large models. But let's say you have your post-training like a 70 billion parameter model. Do you do the mixing experimentation on that like production model, or is like what is the small model version of a 7 dB parameter model that already like knows all these things? Like I guess right now we have things like, model families like Llama and Quen, and I think there's some scaling behavior between them, but the danger is like Quen Quen 1B has seen very different or much less data than Quen 70B or whatever. So there can be more unreliability in that transfer. Sorry, two very long answers. Basically, regression model weakness and scaling laws from small models are the challenges, I think.
I have a quick question. I think I might
Yeah,
have missed this, but what were the behaviors in Almo 3 that you saw were different from previous versions that was probably like an attribution of the data mixing that you guys did?
I think, yeah, this is, I didn't really discuss this. The Olmo 3 mix ended up having a lot more code and math in it. So Olmo 2 was just the natural distribution. So they took, I think, DCLM and a bunch of other things, and then DCLM just makes up 95% of the mix then. And this time we were able to partition a lot of the sources into more fine-grained categories to control things. And
Hmm.
yeah, I think definitely a lot more emphasis on like coding and math, that type of reasoning behavior. It got a lot better.
Hmm.
And I think it's because, at least for mixing, I find that improvement on code and math and more logical tasks is quite easily done with data. It's like a very simple like machine. It's kind of like, at least at pre-training, it's largely more code data, uniformly gives better code code performance. And so it's easy to hill climb on. And so we know that adding more code data will help with code evals versus some of the more like QA and common sense. It's a little bit more murky where um, how models kind of start grokking that. Is it due to compute? Is it due to like really in distribution target data? I think that is there's like a kind of fundamental difference in how models learn from like logical, like models do reasoning or like logic versus like natural language problems. See another question. So, do you have any qualitative insights that makes sense of how your regression model predicts? Like, why should this source be higher than that source? Um, can you elaborate a little bit more on this, Jachi?
Yes, sure. So, because your data sources are categorized by topics, right? So I'm wondering if there's any semantic insights about why this mixing ratio is better than that mixing ratio.
Um, Let me see if I can answer this satisfactorily. Uh, I think there's a lot of like different, so I think depending on how the sources are structured, you can sometimes already predict what the regression model and like the kind of relationship between the mixes and performance looks like. Um, so imagine like a really simple one-to-one world where it's like you have five domains that are like each corresponding to like a separate capability or eval, and you have like five evals. And none of the domains really interact with each other, influence the other evals. And so you kind of have this sort of like, in my mind, it's like a diagonal matrix or like a graph, like a bipartite graph with just arrows going straight across and no other arrows. So in those cases, if every domain only impacts one task or one, metric, the best thing to do would be to do like a uniform mix, because there's just like no interaction. There's also cases where you can think that now let's suppose that your mixing domains are completely unaligned with your downstream tasks. So your downstream tasks are like code, math, instruction following, whatever. And your domains are, let's say, let's say like quality buckets. So like quality bucket, let's say they're scored from 0 to 1, and so it's like 0 to 0.2, 0.2 to 4, and so on. Oftentimes when you mix like that, you will find that kind of the structure is just results in the optimal mix is just like sample from the highest quality bucket. You'll kind of see this sort of like the interaction matrix between quality buckets and different tasks is not going to be very distinct across tasks. It's just going to be like all tasks like high quality data. Maybe there's some difference in rates, but there's no like distinction among the tasks. So I think, yeah, it's a little bit hard to like completely give like comprehensive insights of these things, but these are kind of like two extremes that I like to think about, which is the one-to-one setting of like all domains are independent, all tasks are independent, and then another one where like all domains are like kind of orthogonal to the tasks. And so those give very different regression models, and you can kind of expect what to see and what not to see there. Yeah. Okay, any other questions, or we can wrap up maybe?
Maybe give a minute for someone to stop typing. Mm. Okay, maybe we don't have. All right. Well, thank you
Okay,
very much again, Mike. I'll stop the recording.
yeah.